I've really been looking forward to this event because it's on my favorite topic, and fortunately also on the only topic that I talk about. So it's a pretty ambitious title, yeah. So artificial general intelligence is around the corner. I would say 5 years ago, I would never ever have dared to even mention it. 3 years ago, I would have said it's crazy. And a year ago, I started changing my mind. Yeah. So it's an audacious title, but keep in mind that everything I say today is really relevant for developers, because everything I show you, you can actually go and download it and you can play with it yourself. Yeah? And number two, all of it can be applied outside of gaming. I'm just using gaming because it's more exciting to use as examples, but everything I show can be used in traditional, boring maybe, or maybe not, enterprise applications. Yeah? So a lot of these techniques can apply directly whether you want to sell books for Amazon or get taxes to arrive on time and so on. Yeah? So just to put this in perspective, working for Unity, a gaming company, but my real background is in enterprise. I was head of machine learning at Uber, where I built the Michelangelo platform, which is a machine learning platform used across Uber, both for the app, Uber Eats, mapping, and self-driving cars. Before that, I was GM for machine learning at Amazon. So I ran the elastic machine learning platform for Amazon Retail, used about 100 teams across Amazon for all kinds of purposes, whether that is shoe size prediction for customers or fraud prediction or anything like that. Yeah. I also launched the first machine learning service on Amazon Web Services and was a service owner there. Nowadays, we have lots of machine learning services from Amazon. Before that, I spent time at Microsoft, where I ran the machine learning toolkits team and did other things, a couple of startups, and early on IBM. And because we're in Denmark, I will mention that I actually started out as a software engineer at Brüel & Kjær in Nærum many, many years ago. Unity Technologies, a Danish company, but now headquartered in San Francisco, USA. It's a real-time 3D platform. It's more than gaming, as you hopefully will understand today. We are about 60% market share in gaming. So a game platform, 60% of games are being built on the Unity platform. We are installed on over 3 billion unique devices, and 1.5 billion people play a game developed on the Unity platform every month. I know that because these games talk back to my servers. So I know what you're playing. Okay, so what is artificial intelligence? Is it Siri and Alexa? No, it is not. Siri and Alexa are hard-coded pieces of software. It may use some machine learning to do good speech recognition. It may be using a bit machine learning here and there, but at the very, very basic, it's engineered by people for people. Yeah. I read the other day that Amazon is hiring and plan to staff their Echo and Alexa projects with a total of 10,000 employees. Yeah, a lot of the back end, actually, some of it is actually run by people. It looks like it's a computer doing stuff, but it's really people doing stuff. Yeah, it's very, very people heavy. It's very engineered. Amazon and Netflix recommendations. It's about algorithms. When I talk about AI, it's not about algorithms, it's something else. But our recommendations sort of need algorithms doing stuff that picks, books or movies or whatever it is, that it looks like people like you may also like, but you have not yet purchased, something like that. Yeah. Fraud detection services, equity trading. A lot of people call this AI, but it's really just also smart people thinking out smart algorithms, doing smart stuff, but that's not AI. Facebook feed, not AI at all. And the only AI really successful these days, of course, is job titles on LinkedIn. If you go and look, ask me, because I've looked at it over the years, and now it's like every other title has some kind of AI in it. Yeah. So now I bashed all these things, so what is real intelligence? Well, the dictionary says something like this: it's about acquiring and applying knowledge and skills. That's very abstract, I don't get that either. So what is the real intelligence? What is the real intelligence we truly know? It's the intelligence in biological systems, yeah? So that's the only thing we really know, yeah? So all these definitions of, forget about it, yeah? Animals, humans, we have intelligence, yeah? And why do we have intelligence? Yeah? Because there's a reason. Yeah? The reason is based on a few principles. Underlying all this is entropy. The fact that to maintain complex structures, that requires energy. Yeah? So to maintain a biological organism, we need to consume energy to prevent it from falling apart and become sort of a bland nothing. Yeah? So entropy is the thing that drives it all. So we eat, we consume energy to maintain order. Okay? When we eat, we have to avoid getting eaten ourselves. We may be a plant sitting there trying to get sun, and someone comes by and eats the plant, yeah? It may be a rabbit jumping around and a wolf come by and eat the rabbit, yeah? So there's this sort of energy flow taking place, yeah? We also need to multiply and become more abundant, and all the time we need to be aware of physics. So when we climb the apple tree, we have to be careful not falling down and break our necks, yeah? So it is really about these principles. It's really about these principles and the need to live up to these principles where we need intelligence, yeah? So we have agency where we operate on our environment, we change our environment to benefit ourselves, yeah? So nature invented these kind of things behind me, yeah? Which is fundamentally infrastructure, yeah? So we have chemical mechanisms, we have cellular structures, we have multicellular organisms where we have communication in there, using chemical mechanisms. We have things like the ability to control muscles. We have sensors, touch, sight, hearing, etc. Things like sight came long time ago during the Cambrian explosion. Perhaps maybe just over a period of 350,000 years from light-sensitive cells to the construction of an eye. Yeah? So nature constantly evolved these things to be more efficient. Yeah? So that's where intelligence is coming from, yeah? Period. Yeah? There's a parallel universe somewhere where there's no entropy, we don't have to consume energy to maintain order, and we don't need intelligence. Yeah? We can just sit down and do nothing. Yeah? So, what is more natural that if you want to really invent artificial intelligence, you kind of look at nature and get inspired there. And you look at a 3D engine with a spatial environment, physics engine, gravity, inertia, collision. It's controlled, it's an ecosystem, it's closed, and it really replicates the world, yeah? So think about your game engine as such a biodome for AI experimentation, yeah? At Unity, we have built a open source framework called ML Agents, where you can start experimenting with all these concepts I just explained, yeah? Be aware of physics, don't fall down, navigate, solve problems to achieve something, don't get eaten or shot by some other agent, etc., yeah? So this is nothing new, in a sense. There's been a lot of research in machine learning and AI around visual understanding. So you have like a first-person shooter game where you have a bot trying to be really good at it. You have things like motion control where you have a robot learning to walk, and you have cognitive challenges where you, for instance, have something like AlphaGo, DeepMind's AlphaGo, playing Go. Yeah. So there has been a lot of AI and machine learning research already taking place in these environments. However, they're all somewhat limited. If you look at a true commercial gaming environment like Unity's, and this is not a Unity pitch, this is really about the diversity of the tools and existing assets in the Unity ecosystem, yeah? Then you have something that's way more complex than anything I just showed you that the researchers have been using so far, yeah? So, earlier this year, we announced a partnership between DeepMind and Unity. It's basically fundamentally based on this idea that Demis Hassabis explains here, which is that do not dismiss video games as something that can actually progress AI much more than anything else. So I think that's the most important takeaway today. Do not dismiss it, because it is so close to the real world out there that we have been living in, or not we, but that nature have had around for 500 million years, yeah? It's so close. It has all the fundamentals, yeah? So do not dismiss the idea of gaming bringing value, yeah? So therefore, let's jump to nature's learning method, reinforcement learning, yeah? Because this is for developers, yeah? Almost everything in nature, a little simplified maybe, is based on this idea of observing, taking action, and then learning from those actions, basically what we consider the rewards, yeah? Just like a puppy or a child starts out exploring without really understanding the solution to a problem, we move through this loop, this flywheel, repeatedly, and move from a mode of exploring to a mode of exploiting. Yeah. Yeah. Funny enough, this is also the most used algorithm at Amazon. Yeah? Every single page on Amazon.com is implementing this, yeah? This loop. Showing you stuff, try to get you to click. Whether you click or not, there's a little piece of JavaScript in there so they actually know what part of the page is visible, yeah? Whether you click on this or not matters, yeah? That's the flywheel going around, learning more and more about you, going from exploration to exploitation, yeah? So I mentioned to you that gaming is also really awesome to exemplify some of this stuff that is maybe not so exciting when you look at an Amazon web page and try to understand what's going on. So what we did at Unity was basically to say, can the chicken learn to cross the road? Basically having the computer only see frame by frame, 80 by 80 pixels, and taking, oh, sorry, too fast here, taking 4 actions, 1, 2, 3, 4. We know it means going left, right, forward, backward. Computer knows nothing about that, yeah? And then get a reward signal, which is basically negative for being hit by a car and positive for collecting a gift package, yeah? So can a computer learn to get the chicken to safely cross the road while picking gift packages from Tabula Rasa, from a clean slate, without any kind of software engineers being in here cheating and implementing some kind of smart algorithm, yeah? So let's take a look at the video. This is before training. Notice how the chicken is moving more backwards than forwards. Yeah? It's completely random exploration, 100% random exploration, yeah? But look, in a moment, it will actually hit a gift package right there and then get killed by a car. So within 10 seconds, it has 2 bits of information here, yeah? do that over and over and over and over and over. After half an hour, it looks like this. It gets really good at picking packages. It does get killed once in a while here, but it gets pretty good at it, yeah? And look at sometimes it sort of stops for a moment. Look, oh, and then it got killed again, yeah? Look after 6 hours of training, yeah? It becomes superhuman, yeah? Yeah? It just will keep going. Do you know why it's moving forward? Because I actually never told it anything about moving forward. I just basically said, pick packages and don't get killed. Why is it moving one way? I guess? Yeah. There are always more packages in the future than behind you. This is what I call emergent behavior. This is the future of programming, guys. Yeah? The future of programming is to understand this rewards function. If you haven't heard it before, now you have heard it, and remember it for the rest of your lives. The rewards function is the magic. The wrong rewards function will give wrong emergent behavior. It may not be evident. I will give one example. Facebook had the wrong rewards function, yeah? It was entirely and only dollars, yeah? No bashing of Facebook, but they over-indexed on revenue and got in trouble, yeah? Amazon has a funny rewards function. It's clicks, activity. And then they think money will follow from activity. If we can get people to click on our stuff, they will end up buying. Yeah? A different rewards function. Yeah? I simplified a little, but rewards functions are important. Yeah. So, we have had ML agents out for over a year, and we did some measurements, and right now we are kind of very close, or we are the #1 platform for reinforcement learning in the world. And what you can do is you can use a full Unity ecosystem to create environments with all the graphics and complexities I showed you. You can then train them. We use Google's TensorFlow on GCP, on Google Cloud, and you train your thing, and then at the end of the day, you have a model that you can embed and control your agents with. And that's what I'm going to show you today. Yeah. So let me show you some learning scenarios. Here we have a control or motion control learning. It's basically a four-legged spider, which is by definition not a spider, but a quadruped, learning to walk. Purely the same way that the chicken learned to cross the road. So it tries over and over and over and figures out how to walk. Yeah? So no software engineering here. It's just a naive reinforcement learning algorithm and a very patient computer and an even more patient developer, yeah, figuring this out. Yeah. The rewards function here, move forward. It's basically make progress left to right. That's it. That's the only thing the system is told. Every time it moves from left to right, it gets a reward. Yeah. So a lot of the time it would just stumble around and not figure out how to. It's actually very complex, you know, moving all four legs and figure out to do it in the right order, etc., etc. Yeah? Let me show you another one. Playing ping pong or tennis or whatever. It's basically the goal here is to keep the ball as long as possible. And you see positions of balls and rackets and so on. And here the positive reward is to basically return the ball and over the net, and you have a negative reward if it falls down. And it looks like this, yeah. So these two guys here have learned to play all by themselves. Just like the chicken, yeah. So they just play. We can actually plug out one of the models here and put in a manual game controller and play against the computer, yeah. But it basically learned to play by playing against itself. We had the Soccer World Cup earlier this year, so that inspired us. It inspired us to create a small soccer scenario where we train one machine learning model for a striker, an offensive player. Yeah. So how do we characterize an offensive player? So whenever I put words on this, we have to be so careful because we don't tell the computer any of of those words. Yeah? It's just for us to sort of conceptually understand what we're talking about. The point here is that we train a striker by basically having a rewards function, again, it's back to the rewards function, that is score a goal in the opponent's net, yeah? Score down there, you get a reward, yeah? You can put such an agent into the game here, and they can sort of kick the ball down and score, yeah? We also need a defense. What is a defense? A defense is an agent that gets a negative reward every time they are scored upon. Yeah. And how do we train them? We basically put them together. Yeah. If I have one of them in there, the striker can have an easy time. Then I put the defensive player in there, and now they can train against each other. I will spend a couple of hours in the computer, and I basically have the optimal defense player and the optimal striker, because when one of them gets better, what does the other one? Get a little better too, yeah. So at one point they converge and they can't really get much better. Then I have one team. Then I clone them, so now I have two teams and let them play against each other. It looks something like this, yeah. So again we see emergent behavior. Two extremely simple numeric rewards functions drives the behavior, yeah. Turns out that a defensive player is standing in the front of the goal, like a goalie, protecting the goal. The little white thing is one eye, it's a ray cast. So that's how they look, yeah? Look at the strikers, the offensive players. Why do they look sideways? Why do they not look forward? Well, they look sideways because if you're looking sideways and you're keeping, most of the time you're keeping on the sideline, you actually can view the entire field all the time, so you know what's going on. I find it interesting that with two simple numeric rewards functions, I get something that looks at least like young soccer players playing out along the line, because it's easier to be an offensive player and play up along the line, and goal is standing in front of the goal. Yeah, that after 500,000 episodes of training, this behavior emerges. That is not far-fetched from reality. Yeah? One more inspiring thing, curriculum learning. So look, in this example, we need to have the agent needs to jump a wall. Yeah. When the wall is low, it can just jump the wall and exit. But as the wall gets higher, it gets more difficult, and it needs to use the orange brick, push it next to the wall, jump on the brick, jump over the wall. So it needs a tool to accomplish this. You can learn to do that. What we found is that these systems are much better at learning if you start with an easy problem and then incrementally make it harder and harder, and that progress from one level to the next is upon graduation, when you satisfy certain benchmark. Yeah. So what we do is that first we train it without a wall, it's easy, and then we raise the wall. At one point, it can't jump the wall all alone and needs to use a tool to get over it, yeah? Here's an interesting graph. Oh, sorry, I will get to the graph in a moment. Here's just what it looks like. The wall is low, it can jump itself. The wall is a little higher, it used the orange thing, yeah? By the way, it learns this based on the same algorithms all the time. Everything I showed you is just a very simple algorithm using reinforcement learning here, yeah? So it's very simple stuff. Solves what I think is a fairly complex problem, yeah? Here's an interesting graph. Let's take the orange one first. The orange one is where we take the problem, the most difficult problem. The wall is really high. It needs to move the brick over and so on. That's the orange one. It takes a long time to learn, and it never gets really good at it. It's a little too complex right away, yeah? What we found is, on the blue line, is that if we make it easy to begin with and then incrementally harder and harder and harder, it learns much faster. And the model at the end of the day is much, much more performant, much better than the one if we just jump right into the brute force problem, yeah? or in a brute force solution to the problem. Isn't that interesting? Because that's just how we, kids and animals, they learn. Yeah? We learn in a curriculum, we learn step by step. We don't just go to 12th grade right away and graduate after a year. Yeah? We cannot learn that way. Funny enough, these simple algorithms have the same property. Yeah? So let me jump to something else. This is inspired from biology, where animals and humans, people, we have something called working memory. It's in the software world, in the machine learning world, called LSTM. It's a long short-term memory capability. So here's a problem that the vanilla, the standard reinforcement learning algorithm I just showed you cannot solve, which is, I come into this room, the agent comes in, it sees a big brick in front of it. The brick can be either orange or red. If it's orange, take the orange exit. Red, take the red exit. Yeah? So it needs to remember, because it sees the brick, then it passes it, it doesn't see it any longer, and now it needs to pick the right exit. The rewards function here is very, very simple. The rewards function is +1 if you pick the right exit, -1 if you pick the wrong exit. Yeah? By the way, we don't even tell it. It's the color that matters. Yeah? We just say +1, -1, you go and figure out what I mean by that. Yeah? So standard reinforcement learning will, the moment it doesn't see the moment it passes and doesn't see the brick any longer, it doesn't really remember anything. Yeah? So we need to throw a little memory in there, because that's what we have. Yeah? So we are cheating a little, we are borrowing from nature. So if you add a little memory in there, it can actually, depending on the depth of the memory, for the next 10, 15 frames, actually remember the color of that brick here. So it looks a bit like this. It walks in, sees the orange one, moves to orange exit, walks in, sees the red one, goes to the red exit. Yeah? Okay? The interesting thing here is that, as I said, we're only saying yes or no, good or bad, when it exits. We never tell it's the color. It could have been the shape. It could have been maybe location. I don't know. It could have been something else. It learns to remember the color. Yeah. So it shows you that you add a little feature on top of the basic reinforcement learning capability, and now you can suddenly solve somewhat harder problems. Yeah. Let's show you some of the frameworks that, or some of the code you can actually go on GitHub and download and play with. This is an example of motion control. You know, we're not quite there yet. But it is still fascinating that with a little talk and a little physics, yeah, and then trial and error, these guys eventually learn to walk. You can go and download this software and do this yourself, and now you can start tweaking to see if you can get more natural movements out of it. The problem of these movements are that the physics may not be completely accurate, and there may also be things like we get tired if we would run like that. So sometimes, you know, we would optimize our. There's much more to it than just the physics. Okay, there's also our we want to save energy. Yeah, when we run, we want to run reasonably efficient. Yeah, so maybe having arms like this, probably not a good idea. Yeah, but these guys, yeah, they don't get tired. Yeah. So this is what it looks like in physics. Yeah. So what I want to do now is I want to dive in a little more deeper and getting a little closer to what I was talking about artificial general intelligence. Yeah, and show you an example that would have been very hard to come by in a purely enterprise world. Yeah. So we're talking about extrinsic and intrinsic rewards. So again, when you leave today, you heard me talk about rewards functions, yeah? So just as a few years ago that someone told you about if statements, recursion, loop, for, while, all that stuff, go away and think rewards functions, yeah? Because that's what the future is going to bring, yeah? So extrinsic and intrinsic rewards. So extrinsic rewards are things like capture, achieve, collect. It's doing something in your environment, yeah? You see it often in games where you collect points, gold coins, health points, whatever it's called in games, yeah? It's very specific to the environment. There's something in the environment that you collect and build up, yeah? We compare it to sort of the idea of getting rich, yeah? So getting rich, that's an extrinsic reward, okay? Now, let's talk about intrinsic rewards. So examples of intrinsic rewards are curiosity, patience and impatience, resilience, happiness, love, empathy. Yeah. So let's see. When did you last use those terms in an enterprise application? Yeah. I did not. Yeah. But I will show you an example here of curiosity. So intrinsic rewards are super important. You know why? Because we all have them. And nature is never, never, never doing anything that's not needed. Yeah? So we, and animals, we have intrinsic rewards as well. That's how we survive, back to the basic principles of survival. Yeah? So intrinsic rewards is something nature developed for a purpose. Yeah? They're specific to the agent. And I compare it to sort of getting happy versus getting rich. Yeah? And it may be a bit philosophical, but let me show you. There are limits to standard reinforcement learning. I showed you the working memory extension, yeah? So the ability, reinforcement learning does not have a memory, so now we added memory to it. Good, yeah? Now, when you work in what we call a sparse reward space, a sparse reward space is what I called an Agatha Christie event chain. Anyone in here still read Agatha Christie? Yeah, a little. I wouldn't admit it either. Maybe watch the movies. The problem with Agatha Christie that drives me crazy is these ridiculous, improbable scenarios where something that's super unlikely to ever happen happens, but then something that's also equally, even more unlikely to happen also happens. Yeah? And then all these things that are so unlikely, they also come together in some incredible, improbable scenario, and that's sort of the plot. And it's like, well, that's never, never, never gonna happen in real life, yeah? So think about you being a machine learning system that are in this chain of highly improbable scenarios. So let me give an example, yeah? An agent comes into a house. The house has many rooms. In one of the rooms, in a random room, a push button appears. When you push that push button, a pyramid will appear in another room. There are also some static pyramids around to fool you a little, but a new pyramid will appear in a room. You will have to go and knock over that pyramid and get the gold bar on top of that pyramid, yeah? Okay? So think about that from randomness perspective, yeah? Randomly you come into this house and randomly you are gonna explore the room and find the push button and go through all this chain of events, yeah? I can tell you that with a standard reinforcement learning algorithm, exploring randomly, it will never ever learn it. I think it learned it once after millions and millions of episodes. We tried many times. Just really unlikely that it randomly is going to stumble upon this very improbable chain of scenarios. Yeah? But nature solved this easily. Yeah? Mice running around, rabbits running around, us running around trying to find something. Yeah? We can, as humans, learn highly improbable sequences and the results of them. Yeah. So we should favor agency over randomness. We should basically think about the intrinsic rewards. How can I add something to my reinforcement learning that makes it more efficient? Yeah. So let's add one intrinsic capability: curiosity. And what I show you here is a piece of math. The interesting thing is that we were able to express curiosity mathematically. And there's actually a whole movement now in the AI community. It's called the negative log movement. Yeah. So normally when we do something in machine learning, we always try to minimize the error. Yeah. You want to be as a good predictor as possible. Yeah. So it's always about minimizing the error rate. Yeah. What we found is that let's flip it. Let's maximize it. Yeah. What does it mean to maximize your error rate? It means that you try to make a prediction, yeah, about your environment, and now you're going to pick you're going to learn to pick the one that you will make the biggest mistake around. Yeah. So you're going to maximize. You're going to learn what you don't know yet. Yeah. So what that means is to maximize the error instead of minimizing it, is that we now favor transitions that have a high prediction error in them, where we say, well, I don't know what's going to happen if I do this, so let me do it. It's it's such a simple solution. And let me show you. This is random exploration, yeah? The agent is just, every move is random, yeah? Yeah. It's not really figuring much out here, is it? Yeah. Because there's just no plan. Yeah? It's just random. Yeah. If you were searching for stuff at home, this is probably how I search for stuff at home. This is like it. Yeah. I'm like, oh, I don't see anything. I can't find it. Yeah. Unfortunately. Look at this guy here. This is there's only intrinsic rewards. Curiosity only. Yeah. Look what it's doing. It's not solving the problem yet, but it kind of goes from room to room. It really wants to, now it found the pyramid. It says, what's going to happen if I try to knock this over? It's just a bit more explorative, yeah? It basically goes systematically from room to room. It's just trying to constantly look for what it knows the least about, yeah? Then we put intrinsic and extrinsic together, yeah? So be curious and try to get rich at the same time. And now it's much more directed. It finds the push button, hits the push button. Let's not get fooled by all the other pyramids. I only find the one with the golden cube on. Go and get the cube, boom, solved. New push button, yeah? So I was having lunch at a conference 2 months ago. One of these American lunches with a round table and everybody sitting there and talking, and the professor told me that there's limits to reinforcement learning, there's, sparse problems can't be solved, clearly we're going to enter the next AI winter, yada, yada, yada. I'm like, no, I don't think so. This is a very complex problem here. I gave this talk a few months ago, maybe 4 months ago, and a month ago, a couple of folks came back to me from a company in France and said, "Oh, we're actually implementing this in our recommender." Yeah? So instead of picking random movies or random books or random products to show you, yeah, what the system needs to do, it needs to look at the whole product catalog and say, "Woo, I have never seen you ever touch a sci-fi comedy book. Let's try. Let's try that one. Yeah? Let's try the most improbable product first, and then let's work through it and learn as much as we can about you, yeah, by being curious, not random." Yeah? That's that's a very important observation here, yeah? Just by adding one intrinsic reward. I didn't go on Wikipedia and you'll see these intrinsic things, and people argue, are there 8, are there 40? I don't know, yeah, okay? So, let's do something that's a little more fun. This is Popo. Popo is a virtual mechanical dog, yeah? It has joints, small motors, and what I'm going to show you is, here's a game character, and it can learn to walk, run, turn, jump, everything, yeah, on its own. So no humans ever did anything to this dog, yeah? It's pure reinforcement learning, and there's only one reward: bring back the stick, yeah? So we sent the dogs in training camp, and you can see they're not really good at moving yet, yeah? Yeah? They can nothing. There's no animator here, there's no software engineer who said you need to move the legs like this, and it needs to look this way, etc. They just try over and over and over, and at one point it looks like this, yeah? This is completely machine-learned character, yeah? I throw the stick with the mouse, it goes and fetches the stick. It learned to move, yeah? Yeah? It's not perfect, or maybe it is, who knows, yeah? Drops the stick, I pick it up, look what happened there, oops! Yeah. And it hits the stick, and yeah? I mean, like, there's no artist here, there's no software engineer who basically figured it all out. There's only TensorFlow on Google Cloud figuring it all out for us, yeah? 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 I can even take this fella and put it on a phone. That's why I said, you build the environment, the grass and the dog, you train it, you have a model, you put it on your Android or iPhone, and it plays there with, yeah? You have one model of a dog chasing the bone, yeah? Why not have 10, yeah? What you have here is you have 10 machine learning models directing each dog individually. They take space up, but they all want the same thing, yeah? Again, it's not coded, it's learned. Now we have 50 of them. Look what happens out on some of them out on the side there. Look, do they fall over? Yeah. Oh, there we go. Yeah, you get pushed and fall over. It's all physics in place. Yeah. Traditionally, what you do in animation, in this case, is that you would normally implement some crowd algorithms. Yeah. But here, it's just interaction between 50 models and physics. Yeah. Okay. We have tons of environments. There are more environments than on this list here. You can go and download it all on GitHub and play with everything I showed you is there, including curiosity. Yeah, it's there. Yeah, so it's easy to use, and it's kind of pretty leading research when it comes to machine learning and AI, and there's so much more to come. Yeah. Biology has a fantastic trip in store for us, yeah? Attention. Did you know that an Uber self-driving car has 600 sensors? Yeah? 600 sensors. It has 16 cameras looking as much backwards as forwards when it's driving. Yeah? Nature invented attention, because otherwise our brains would be like ginormous, and you spend, will be 2 kilowatts and not 20-watt computers, yeah, up here, because we would have to know everything going on all the time. Attention limits the energy consumption to basically focus and just process what's important to us, yeah? So we could learn from that. One-shot learning, there are things you learn once in life, like put a finger in the candle when you're 2 years old and you will never ever do it again, yeah? Working memory, I showed you working memory, that's the LSTM. Continuous learning, the thing that, you constantly learn, which is really, really tricky, also in humans. Yeah? When you're a kid, you're really good at learning new stuff. You know what happens in machine learning models when they're really good at learning new stuff. they forget the stuff they just learned. Kids the same. I had kids who spoke fluent Japanese because we lived there, and then we moved to the US, and 6 months later, they couldn't even count to 3 any longer, yeah? Later in life, we are less elastic in our neurons, so we don't learn new stuff as easily, but we don't forget as easily either, until actually later on, but that's a different story, yeah? Imagination, it always bothers me when I see people saying computers don't dream. That's the only thing computers do, yeah? You run simulations. It's dreaming, yeah? I talked about intrinsic values, yeah? I didn't show that, yeah, I have another demo of hierarchical learning too, which is a lot, we do a lot of that, where our eyes is doing one thing, and then they tell our body to react to that. So you have a decomposition taking place. It's very, very efficient, yeah? So all these things I showed you here is basically inspired by biology, easily to implement in a game environment, and then you can really push the boundaries, yeah? What I want to say here is that's just biology, yeah? And I want to leave you with just one thought here, which is the human brain today, the last 100 years and the last 1,000 years, yeah? The human brain is the same as it was 50,000 years ago, or 100,000 years ago, yeah? So the human brain 100,000 years ago were exactly as capable as our brains today. The DNA has not changed, yeah? So what is it that led to this dramatic revolution in our abilities, 20,000 years ago, 10,000 years ago, maybe agriculture was 10,000 years ago, the scientific revolution 500 years ago, and things move exponential. Yeah. If our brains have not gotten smarter, because they have not gotten smarter, the same processing power is in those brains. Yeah. What is it? Yeah. It is that they find interesting ways of working together, creating tools that do not get forgotten and are being reused by other people standing on mentally on the shoulders of each other, yeah? So, everything I showed you today, with curiosity, long LSTM, all these techniques, yeah? It's really just single agent behavior, yeah? The 50 dogs or the 50 puppies you saw running, they are individual, they're just taking up space, but they're not cooperating, yeah? So, when we get to artificial general intelligence, yeah, that's when all these agents start cooperating. Yeah? And we have not really explored that yet. We will. Yeah? That's what's going to happen over the next few years, is that we're going to start stepping out of this. I'm going to get this single machine learning model, I'm going to get this single computer to do this thing, where we're going to say, I'm going to have 1,000 machine learning models working together to solve a problem. Yeah? So draw the analogy here between the human brain and its exponentially increasing capability of doing things without the individual brain being much smarter today than it was 50 or 100,000 years ago. Yeah. So let's learn from biology, but let's not stop there, and we won't stop there because we'll start moving into other aspects of how to create incorporating systems. So that was all I had for you today. Welcome to Connect. I think we have some time for questions. Is that right?
Yes, we do. But can we do first a round of applause for Donnie?
Thank you.